Yeah, so now recording is on. Thank you. I totally forgot
No,
about.
thank you to you because we are able to at least to watch it again.
Yeah, sure. Okay, so let's just make a quick recap then, because the start was unrecorded. But first I set the, oh bugger it. So does it not want to let me change the style? Yeah, looks like that. Okay, so I'll just go back one step. Ah, I see now what's wrong. So let's delete this. So one more time, what we did, we kind of simulated the coin tosses here and counted the number of times each outcome occurs, heads and tails. So we counted the frequencies, in fact, and we found the relative frequencies in percentage. And we can see that the more events you get, the closer your frequencies are to the, what do you call it, to the probabilities. So let's make another chart, shall we? Let's make another chart. I will do it like this. So maybe we can go like 2, 4, 6, and so on. So let me put these auxiliary numbers here. We will need it to automate the process, and we can go all the way up to 200, I think, but yeah, why not? So 44. Now let's make the steps a bit larger. So 4, and I will add 8 each turn, or maybe 16. Yeah, let it be 16. So 4, 20, 36, 52, and so on. And I will expand that till we reach 200s. Okay, 196 is good enough. Yeah, okay. So what shall I do now? I'll ask Excel to count the number of heads, count if starting with A1. Oh, yeah, well, it won't work that way. Sorry. So what can I do? Oh, I can do it like this. I can do it like this. So yeah, sorry guys for this dithering around. It's just, it was a momentary idea and not prepared in advance, and that's why it's making me kind of rumble here, wasting the time and so on. Okay, so let's go. So here I will take first 10 cells, the first row. So it's starting A1 and ending with A10. Oh, sorry, J1. And I will count everything, every cell which contains heads. And we have 10 cells there in the first row. So I'll divide this by 10 to get the percentage. So you can see exactly half of this row is heads. So we have 50% here. Lucky for us, it's not always the case. So let me make it into percentage. Okay, so now here I'll do the same for next row, yep, which is B2 up to B oh, J2. Oh, sorry, A2 up to J2, but it will be only one row. So I want to get it like this. Oh, by the way, yeah, let me just put a $sign here, and then the number will not change. And we will have 20 cells for 2 rows. Okay, and now I guess we can just go on. However, these numbers will have to be changed by hand. 30 cells. So in fact, what I'm doing is okay, so this can be automated too. Yeah, now now it's all right. All the way up to 200s. So these are the percentages for heads. And now we can do a neat graph here. So it's here, I guess. Yeah, I'll take a scatter with smoothed out lines. So you can see that at first, when we have smaller numbers, like between 10 and 20 or between 10 and 50, it's kind of jumping around. It's still close to 50, but not very close, and uh, it's oscillating around that, not around that value, near the value of 50%. But then when you get more and more coin tosses, when you get larger numbers like 100 or 150 and so on, the line smooths out and it remains more or less close to 50%. It won't be exactly 50% always. Well, it can be sometimes. Yep, there will be times when you will get exactly 50%, but most of the time it will be just some number which is close to 50%, but not exactly 50%. So if you take, for example, maybe 10,000 coin tosses, then the difference between the frequency and 50% will be very, very, very small. So here you can see we have 2% or 1% differences. If you take 10,000 coin rolls instead of 200s, or maybe 200,000 and so on, so large numbers, you will have something like 50.001% or maybe 49.9995% and so on. So it will be more close to 50%, to your probability. And that's called the law of large numbers. And that's where this abstract mathematical toy, which is the theory of probability, turns into something practical. So let's say, what can we do as an, what can we take as an example? Well, I don't know, maybe, so maybe you are some crackpot supervillain, yeah, like Two-Face from Batman, who decides his actions by tossing a coin. You cannot predict a result of one coin toss. You know that there is a 50% chance to get heads and 50% chance to get tails, but you don't know what exactly will you get when you toss a coin one time. And that's completely random and unpredictable. But let's change your modus operandi a little bit. So you are still a supervillain who uses coin to decide his actions, but instead of doing one toss, you make 100 coin tosses and then choose your actions. And in that case, you will be just unable to choose because your outcomes, you will have as much heads as tails. Well, there will be still small differences, but If you just round up, you will get 0.5 and 0.5 each time. On the other hand, so let's say that you are using one coin toss instead of 100, and each time you get heads, you do something bad. Each time you get tails, you do something good. So somebody who knows about that rule of yours can be pretty sure that you will do as many good things as bad things, because he knows that when you have a large number of coin tosses, half of them will be heads. Not exactly half, a little bit more than half or a little bit less than half, but still very close to a half. Well, that's kind of impractical example, but there are times when the conjunction of probability theory and the law of large numbers are used with the very tangible, practical implications. So one example will be physics of the gases. So we have all those cars around now. Yeah, well, if it's not an electric car, then it will have some kind of a reservoir where you burn the I forgot that word. Okay, so you will burn the gasoline, maybe spiritus if you are somewhere like South America. So you will have that. Excuse me. The word fuel. Yes. So you burn the fuel to extract its heat energy and turn it into mechanical energy, which will move your car. But how can we be sure that the fuel gases will behave the way we want them to? Because you see, if you take a gas or a vapor, it consists of millions and millions, even billions of small particles, and each of those particles acts in almost completely random way. You cannot predict the movement of each particle, but the fact that there are billions of particles makes it so that we can use law of large numbers. So we can calculate the probabilities, and as there are a very large numbers of particles, we can assume that those probabilities will be identical to the frequencies. So we can say that if we have only one gas particle, we can tell nothing about it except probabilities. But if we have billions, we can say that approximately 1/6 of their total number will go to the left, and it will push the piston, which will then turn the wheels and will make our cars move. So that's one example. Another one is financial analytics. So you cannot tell anything about one separate seller on the market. The seller is a living man, and living men are kind of unpredictable most of the time. So you would assume that they will act rationally to maximize their own income and so on, but that's not always the case. We humans are crazy random guys some of the time, and unpredictable at that. But when you have a market that consists of thousands of sellers, then again, the law of large numbers comes into the scene, and you can use it to predict something about the market. And that's the way most of the financial analytics works, and that's how successful brokers make their incomes. yeah, on the stocks markets. Well, not all of the brokers use statistics and theory of probability concisely, but most of the time their mind does it, even if they themselves don't know it. In next topics we will move to that. So for now we have the law of large numbers. We know that when you get large numbers of events, your frequencies become approximately equal to your probabilities. So that's one way of approaching the problem, but we can turn that thing in opposite direction. So let us make a 5-minute break. So I will come back after 5 minutes. And during those 5 minutes, I would ask of you to think a bit on what can be the opposite of this. So we know the probability and we can deduce frequencies using law of large numbers. Can we find the probabilities if we know the frequencies? Again, using the law of large numbers. Just ponder on it a little bit. So I'll be back in 5 minutes and we will go on. Okay, I'm back. So that's one way of using law of large numbers. If we know probabilities in advance, we can imply frequencies using the law of large numbers. However, in real life, it's not always possible to know probabilities in advance. So for a coin, we can be more or less sure that probabilities are 50% each, yeah, for heads and tails. For a dice, we kind of know that probability of each outcome is, what do you call it? 1/6, all right? And we tell it, we know it based on frequencies, or based on symmetries, based on geometry, in fact. But sorry, so there's something strange happening. Okay, I guess now it's all right. So for the coins and dice and some, well, what do you call it? Some simpler systems, you can just imply probabilities like coins and dice, as we already said. But there are cases where the probabilities themselves are unclear. Maybe the most simple example will be, I don't know, maybe we will look at probabilities of a child being a boy and or a girl, yeah? So the school course of biology tells us that the biological gender of the child is determined by chromosomes it takes from its parents. So if you have a combination of X and Y chromosome, the child will be a boy, and if you got X and X, it will be a girl, or she will be a girl. However, we don't know the exact probability for each combination. If we just look at how that can turn out, yeah, let us do Let us do a simple picture. So give me like a minute or so to prepare my screen. We will look at real life example. The science guy is doing biology encounter all the time. So, okay, clear the screen and share the screen. Shall I? Yeah, it seems for some reason, that's strange. Why? Yeah, I guess now. Oh, uh-huh. Yeah, sorry. I don't know why, but now I cannot change the settings of screen sharing. Well, okay, that will do. Let us try. So, we have a father, and he has XY chromosomes because he's a biological male, and our mothers have XX chromosomes because they are biological females. And now, when the child is conceived, we can have all the different kinds of outcomes. So let me put it this way. Oh, and I'm not sure that I'm looking at all the possible combinations here, but I guess that will do. That should be enough. So here we have 4 possible combinations. Yeah, mother's X chromosome can couple with father's X chromosome, and in fact each one of those can couple with each of those, so we will have 4 instead of 2. 4 combinations which are XX. Here on the picture we have only 2 of them using one of mother's X chromosomes, but there is a second one which will give 2 more. And we have 4 more combinations which gave us XY. So here we have, oh, sorry, I put it in the wrong place. So this one is a father, this one is mother. Yeah, I don't know why did it cut off like that, but okay, whatever. So in this case, when you have 2 X chromosomes, a child will be a girl. And when you have XY, child will be a boy. And we have, so 4 here and 4 here, 8 total combinations. 4 of them give us a girl and 4 of them give us a boy. And we can assume that the probabilities will be again 50-50. 4 over 8, which is 50%, and 4 over 8, which is also 50%. But it appears that that's not the case. So biologists tell that those probabilities, those combinations are not equally likely to happen. So there are some additional factors like the hormonal background of mother, the state of the womb, maybe the quantity of some, oh, again, I lost the word. So quantity of some chemicals in the blood which make one of those combinations more likely, and it depends on the outside conditions like the accessibility of a food, the time of the year, even the social unrest and so on. And that will shift the probabilities. So we cannot tell in advance that the probabilities are exactly 50-50. What we do in such cases? Well, what we do is we study the populations from different countries, from different places around the world. So we take, for example, 10,000 children which are born in Uzbekistan, and we count how many boys and girls are there. And then we do the same for maybe for USA, for Zimbabwe, for Mongolia, for Japan, and so on. And we find those percentages everywhere. And then we say, hey, look, there is a law of large numbers. And that law of large numbers tells us that these frequencies should be approximately equal to the probabilities. So if we average over all of those percentages we get for different populations, what we get should be approximately the probabilities. And by the way, that shows that probabilities are a bit higher for a boy. So there is a 51% chance, not 51, it's between 50 and 51, but it's more than 50% chance that the child will be a boy, and less than 50% then it will be a girl. So there is a difference, very small difference, but it's still there, and it's found exactly by using law of large numbers. So maybe we shall try to do something like that in practice, and I guess, yes, let's just go and do that. So I will stop this share. I will switch back to Excel. Oh, it does not want until I stop. So share screen, back to Excel. So I'll create an example data set here. So let's say we have two outcomes, A and B. And let's pretend that we don't know the probabilities for each of them. But we have a large number of trials where we got all those outcomes. And here we have, so let me count them. So we have 25 rows and 9 columns. Oh, well, 9 is a small number, but okay, it will do. So 25 times 9, it's 225. So 225 trials here, and let's count the numbers of each outcome. So count if, so I'll count all the cells in this range which have A in them. Oh, why is it not doing that? Oh, okay, because we have an excess equal sign. So A, B. So let us do the same for B. And then we can count the percentages. So I'll divide the number of A's with the total number, which is just number of A plus number of B. And I will do the same for B. We have to change it a bit, so it's 46 and it's 47. Okay, let's turn them into percentages. Now we'll round up. So it's approximately 27 and 73. If we had larger number of outcomes, these numbers will be slightly different, but still, we can assume that, well, the probability of outcome A is somewhere around 27% and probability for B is somewhere around 73%. We have absolutely no way of knowing that in advance. We can only study the data and find out that, yeah, probabilities are about this. And those numbers are not precise. They are not precise. We can be always sure that this is not the exact probability. Maybe the true one is 30% or 25% or 26 and so on. But still they are close. And if we had, so here we have 225 numbers, but if we had something like 20,000, then we will be pretty sure that these percentages are very close. So here, the difference is significant. If I go there and look at the formula, I see that probability for outcome A is 25%. I just chose it to be that way. And here we have 28 now. Well, it changed to 28 and 72 because each time you change one cell, all the random cells will be changed by themselves, but no matter. So we see that there is indeed the difference. The true probability is 25, and we get 28 here. If we look at the smaller numbers, so here I have all the 225 numbers. If I take just first 10, what will happen? So I'll just, yeah, let's just do it again. So count if, take only, oh, it's not 10, it's 9, but it doesn't matter. So first 9, I take all the A entries in first 9, I divide by 9 to get the percentage, and it's 33%. Let me turn it into percentages again. So it's 33%, and this one should be like 67%. Oh, now it changed because, yeah, it generated all those random things again. So it's not 10, it's 9. So you can see when we have larger number of entries, hey, why does it, is it correct? Yeah, looks correct. So when you have larger number to study, you get more correct predictions for probabilities than in case of small numbers. So let's look at the extreme case. Let me take first 2. So that's kind of ridiculous. Yeah, 2 is not a proper number to do statistical studies, but just for the case of example, let's take first 2. And so now you see, if you take just first 2, we have 0 frequency for A, which implies that the probability for A is 0, but in fact it's 25. When you take a slightly more, so first 9 entries, the percentages are closer to true probability, which is 25%. And when you get 200 and something, you get even more close, and so on. So that's the gist of what you will be doing. Most of the time, like mathematicians working in statistics, they know probabilities in advance, and they use that to to deduce something about frequencies and so on. But those who will be working with real life sciences like physicists, chemists, economists, all those social sciences guys and psychologists and so on, they work the opposite way. So they study the population first, they get the frequencies, and then they deduce the probabilities. And maybe then they will use it for their theories or for their analysis and so on. So that's the essence of the law of large numbers. Now, there is one more thing that we can do. So we have those tables like heads and tails here, or A's and B's here, and those are kind of large numbers, large tables with lots of entries, and just looking at it, you get lost. So there are too many things, and our minds are not used to look at that amount of data and just see everything. So we need to find some way to maybe illustrate that in a way that is conceivable for human mind, like here. So we have this pretty chart, right? You can look at that chart and you see that, oh, okay, so approximately the 60% of all the entries are heads and about 40% are tails and so on, without looking at each entry. So these kind of things are useful, and we need to know how to build them. So this was very, what do you call it? Simple example. Simple example. Yeah, we have only two outcomes and so on. Let me create something more complicated here. So right now we don't need to know what do those comments mean. I will just use them, and in a time we will come to their meanings. For now, I'll just create some random data set. Maybe, okay, let it be 50 and 5 and oh, no, that's not the true way of doing that now. This one is better. So maybe 10. Maybe 0.2, I don't know, and random. Okay, so let's look at this thing. So I have 150 numbers here. Those are just some random numbers out of thin air without any meaning. But let's pretend for now that they convey some sort of meaning, that they have some importance, that they are somehow connected to real world. And we need to study this set. So again, there are too much numbers. Looking at all of them, you get lost, but we have a way of illustrating it in some ways which are kind of easier for humans to perceive. So one way, the easiest one, will be entering all of those into Excel, marking them out, and then asking the Excel to create a histogram for us. Well, here it won't be so much informative. So what's the meaning of this? So essentially what it's telling us is that there are 6 numbers between 0 and 1.8 and 7 numbers between 1.8 and 3.6 and about 2 numbers between 3.6 and 5.4. That's not correct. So we get 13, 15 numbers in total. Oh, okay, it did take only 1 column. Yeah, we will have to do it. We will have to do it manually. So let's find the minimum and maximum first. So smallest number in this set is 0. The largest one is 5. By the way, am I not missing anything? Okay, so we have numbers between 0 and 5 here. So let me create some kind of a table, 0, 1, 2, 3, 4, and 5, and count number of entries. So we can do it by hand. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 entries of 0. But instead, I would just ask Excel to do that, because I'm a human, I'm imperfect, and I'm prone to errors. Yeah, you see, I missed 1. I counted only 10 while there are 11 of them. Okay, so we will ask Excel to count each entry. Oh, and instead of that 0, I should put the table. Okay, now it looks all right. So we have 11 zeros, 40 ones, 49 twos, 29 threes, 14 fours, and 7 fives. These numbers, how many times we encounter each entry, are called frequencies, as we have already said. Just for another example, there were frequencies here for heads and tails, and here we have frequencies for those numbers between 0 and 5. And we can find relative frequencies if we want. So let's find the total of all those, the sum of all those. 150. Oh, okay, we already knew that. Yeah, 15 rows and 10 columns gives you 150 numbers. Whatever. So if I divide each frequency by the total number, what I get is a relative frequency. You can leave it as it is, like a decimal number, or you can turn it into percentages, whichever you prefer. There is no hard rule to use this or that. So both percentages and decimals are okay. Okay, so here it is. So that's the minimum amount of data we can have about this set. Yeah, we can't see all the numbers from this table, but we know that, okay, about 7% of entries are zeros and 32% are twos and so on. So we know something about the data this way. And this thing is called frequency table. So it's frequency table. Well, but still it's some kind of numbers and so on. And not everyone likes to look at numbers. So one more thing that we can do is we can create a graph. So this thing is called frequency polygon. Oh, can I not change it now? Oh, okay, whatever. So it's frequency polygon for our data. In fact, it's giving us the same information as this table. So we can just look and say, okay, so there are about 10 entries of 0, about 40 entries of 1, and so on. So this and this are the same thing presented in different ways. When you are, maybe you are doing some kind of market study for your company, and you are going to present it to the board of directors. Most of the time you will probably go with this kind of charts instead of bringing this kind of large tables. So there are, let me show you what you can encounter in real work. So there are some examples in the textbook. I will open it now, and then we will look at it. So I guess it was chapter 1. I guess it was chapter 1. Frequency tables, frequency. Okay, it's chapter 2. Yeah, here it is. So I'm closing this and I'm switching our screen share to oh, where it is. It won't let me choose the, okay, doesn't matter. So here we have our textbook by Mr. Douglas Link, and that's the example data sets. So each of those numbers is a profit on some cell. So there is a made out fictional automobile trade group called Applewood Auto Group. And so here we can see, for example, they sold some car. We don't know what kind of a car it was, but they made a profit of $1,300, approximately $1,400. And they sold another car and made $1,700 of profit. And they sold, and so on and so on. So there are some cells which made very little profit, like this, $369 only. There are some which brought them more money, like for example this one or this one, almost $3,000 and so on. So this kind of data, it can be used excuse me, it can be used to study your sales if your company is performing sales. So you can study your sales and you can decide which range is bringing you more profit, where you should expand, where you should cut out, and like that. However, yeah, we got a bit carried away, and some of you might be thinking, hey, we were talking about probabilities, and all of a sudden now we are here dealing with large tables. What happened? So what happened indeed? We will almost never use the probability for a single event. You will never be interested with an outcome of one coin toss or I don't know what, with one event. But you will use these laws and principles for big amount of events, for large numbers. And that's where probability turns into statistics. So statistics is all about dealing with data, with large amounts of data. So you have two different kinds of statistics. So first one is descriptive statistics, which only bothers itself by describing the data, like we did here. We said how many of each entries are there, how does our data set look, and that's all, right? It just tells you something about the data, which you can find out yourself, but here it's just presented in a more accessible way. And that's the descriptive statistics. And then there's a thing called inferential statistics. So inferential statistics lets you use something that you already know to find out something that you don't know yet. So maybe these parameters, these things about the data can be used to discover something new. It's not always the case, but sometimes it's the case. Sometimes you can use the existing data to discover a new data, a new knowledge, new laws maybe. And when it's possible, it's hell of a useful thing. So for now, we will focus on descriptive statistics. We have already started it, in fact. So we looked at how to present our data, two types of presenting. Yeah, we have our frequency table and our frequency polygon. We will look at the measures of data, which are also part of descriptive statistics. That will be our next topic on Wednesday at 1 p.m. So there are some parameters. So instead of looking at each entry and so on, you can do it the other way around, right? So I won't bother with this table now. I will go back. So here we have possible results of a dice roll. It can be 1, it can be 2, 3, 4, 5, and so on. But instead of saying that you have these 6 outcomes and each of them has this probability and so on, you can just say that an average result of a dice roll is 3.5, and that's a measure of data. So we will look at it at our next topic, the average value or the mean value. And there is a thing called median, there is a thing called mode. We'll go through all of that on our next topic. And that's also a part of descriptive statistics. And the next week, our first topic will still be in descriptive statistics. So we will look at measures of spread of data, like there is a thing called a variance, a range, and so on. And then we will start slowly making our way into inferential data, and we will look at how to use the data to predict something. Okay, but back to our descriptive statistics. So these are two ways of presenting the data. There is another way. Well, here you have distinct values. Yep, you can have 0, 1, 2, 3, 4, and 5, and nothing in between, and nothing except them. But that's not always the case, and now I will create another example data set. Yeah, maybe it will be 20 and 5. So I will create another example data set. There will still be 150 entries. However, the numbers themselves will be a bit more this time. So I'm not sure if that's the correct number. Let me check. Oh, it's only 11 rows. So we need 4 more. Yeah, okay, here we have it. And let me change it to be only one decimal. That does not matter, in fact, but let's just make our job a little easier. Okay, so here 150 numbers again, but there is a difference between this and this. So here every entry is unique, and if you want to do something like this, yep, taking each entry and finding its frequencies, you will have, well, we have 150 numbers, and maybe we will have 50 rows in this table, or 100 rows, or maybe 150. So frequency table will not do our job easier here. So instead, what we do is do something similar but different. So again, let me find the minimum and maximum value. Okay, smallest number is 6.6. The largest one is 34.6. Yep, so this is minimum and this is maximum. Oh, that equal sign ruining my life. So why are we doing this? Why we don't do this? Why we don't just make a frequency table? So look, the smallest number is 6.6. Let me write it here for now. I'll erase it afterwards, but let me just put it here for now. So next one is 7.5. Yeah, looks like so. 7.5. And then we have 8.3. So I guess you already see where is it going. So we need to find each entry and put here. So 9.3 here. It's already 4 rows in our table. And then the next one is okay, even finding it is kind of a tedious job, but I suppose it's 10.8, right? And if you look here, there is only one 6.6. There is only one 7.5. Only one of these, and this. So if that goes on like that, then I will just have a table which will have 150 rows, and frequency for each row will be 1. And that's just meaningless. Here we had 150 numbers, but we were able to turn it into a neat table with only 6 rows. Yep, so 12 numbers instead of 150. Or if you count the percentage at separate numbers, then we have 18 numbers. It's still much less than 150. So we simplified the presentation of data. But here, if you just do the same thing as here, you won't have your simplification. You will just have the same 150 numbers written in a single column with additional ones. We don't want that. We want to simplify. So instead of doing the frequency table, I'll do what we are doing now. So I found the minimum and maximum. Yeah, 34.6 and 6.6. I find something that's called range. Well, it's just max minus min. That's the range of the data. And in our case, the range is 28. Okay. And now I want to divide our data into, well, what do you call it? Into an intervals. So let me try sharing the screen again. I guess that should be possible now. So I'll stop this. Yeah, now it's working. Now it's working. So I'll move here. So back to our example with 0, 1, 2, 3, 4, and 5. Yep. Our data looked like this. Oh, just a moment. Let me set up. I might be, yep, okay, it's all right. So you have separate data points. Zero, 1, 2, 3, 4, and 5. And we have seen that there are different numbers, different quantities of those numbers. So let me look at the Excel just to deduce. Yeah, okay, so we have 11 entries here for 0. So I won't draw 11 small dots, but I guess you get the point. So 11 zeros here. We have 40 ones and so on. We have 49 twos, but the thing is, you have only only 6 categories. This, and this. And you can just count everything. But in the second case, so our data is not in separate points. So it starts with 6.6. It ends with 34.6. Small technical difficulties. Okay, now it's all right. So 34.6. But instead of having separate dots, as in this case, we have, oh, yeah, excuse me. So we have all the possible numbers in between. You not only have this, and this, and this. You have this one, too, and this one, and this one, and this one, and this one. So everything in between. But I want to do something like this, where we had separate points. I can't have separate points here, but I can take this interval and divide it into several groups. So maybe I can divide it into, so maybe into 4, right? Well, so if those 4 were equal, then this one will be 13.6, and this one will be 20.6, and this one will be 27.6, and then 34.6. Just an example for now. And again, if you go here, you have 11 entries of 0. Here we don't have such thing, but maybe we can count everything between these two. So maybe you have 1 6.6, you have 1 well, we were looking at that, wasn't we? Yeah, we have 1 7.5, 1 8.3, and so on. And we can still count them. Just instead of saying that there are, yeah, just as an example, instead of saying that there are 11 entries of 6.6, we will be saying that there are 11 entries between 6.6 and 13.6, or something like that. Well, here I chose 4 intervals just as an example. In fact, there is a rule that tells you how many intervals is optimal to have. That's not a hard set law, but that's more of a recommendation. And well, we will look at that now. So back to Excel, I guess. So back to Excel. So here we have 150 numbers. Let me put it somewhere here, 150. The information theory, so there is a branch of mathematics which is called information theory, tells us how many into how many groups we should divide our interval. So we have 150 numbers. We should find such a number k that 2 to the power k is less than 150, and 2 to the power k plus 1 is more than 150. Okay, why is it so? So I guess more or less all of you know about bits, like right? So you had your informatics classes at schools. Maybe you did not use computers on them. So just as an example, my school had maybe 2 old private type computers, and we wouldn't use them on our information science lessons, but still they taught us about about some programming languages, about the measuring the information, about bits and bytes and so on. So bits are in fact binary digits, and they are the least possible measure of information. So you can imagine a bit as something which can be defined by only asking a question which requires the answers like yes or no. So for example, if you want to know my age, you will most probably ask, how old are you? And I will give you the number. But there is another way of doing that. You can ask me if I'm older than 30, and I will ask yes or no. Oh, I'll answer yes or no. Let's just imagine that I answered no. What will you do? What will be your approach? So you know that well, that's not true, but for the case of illustration, yeah, you asked me if I'm older than 30, and I said no. your next step will be asking if I'm older than 15. Most probably the answer will be yes. And then you will find what's in between 30 and 15. So in this case, it's 22. Well, it's 22.5, but doesn't matter. So you will ask if I'm older than 22. And maybe I'll ask yes. So you are only asking the questions of yes or no. And in the end, you will close on my true age. Well, and if you are looking for an age between 0 and 32, you will need 5 questions, which only require yes or no as an answer. And if you are looking between 1 and 150, or between 0 and 150, you will require this number of questions. Yep. So this K can be imagined as a number of yes or no questions you need to ask to find out a select number between 0 and 150. So in fact, that is how many bits of information are there in 150 numbers. And you should divide your interval between minimum and maximum into as many chunks, as many bits of information are there. That's the reason for this. But yeah, we got carried away. Let's just find that number. So I know that 2 to the power of 7 is 128. And I know that 2 to the power of 8 is 256. And 150 is right between those two numbers. So that tells us that our K should be 7. So let me put it like this: number of intervals, or number of data bins. Those chunks, those intervals are called data bins. You don't have to memorize all the powers of 2. So you can just do something like this. You can calculate the logarithm of 150 base 2. It will be a decimal number, as you will see. Yeah, it's 7.22. And you will just drop the decimal part and take the integer part, which is 7. And that's exactly our K. Okay, so we have our interval between 6.6 and 34.6. Our range is 28, and we should divide that interval into 7 data bins. So I need to find the size of one data bin. And for that, I will just divide this by, so I will divide the range by number of data bins. And in our case, it will give us a pretty number, the 4. Most of the time you will get some kind of decimal number, and in that cases, when you have decimal numbers, it's better to round them up. So just an example, if you get something like 3.78, you better turn it into 4, or maybe even into 5. Okay, so this number is the minimum size of data bin. You can get the size of your data bin to be larger than that, but you can't get it to be less than that. And in fact, we will make it larger. So, but first, let's just see where we are going. So I have this 6.6, right? So my first interval will be 6.6. So it will start with 6.6 and go up to 6.6 plus 4, which is 10.6. And my second interval will start with 10.6 and go up to 14.6 and so on. So 14.6 up to 18.6, 18.6 up to 22.6, and 22.6 up to 26.6. So the next one will be 26.6 up to 30.6. And we have only 6 intervals for now, and 30.6 is not in our set yet. So the next interval will start with 30.6 and go up to 34.6. And then we will go and count how many numbers are in each interval. So again, we can do it manually. So for example, 1 for first interval, 6.6, it's 1, 7.5, it's 2, 8.3, 3, 4, and next one is 10.8, which is not in this interval. So we have only 4. And we want to do that for each interval. However, there are 2 issues. First, oh, what did I do? Okay, it's not me, it seems. Okay, whatever. So, our first issue is one of our numbers, which is 34.6, is not still in our data. Yep, it's outside the boundary of last interval. It's not inside it. And for it to be inside, I'll need to add another interval which starts at 34.6 and ends at 38.6. But I should only have 7 intervals. So that's one issue. Another issue is those numbers, those pesky decimal numbers. I want pretty nice numbers, not these decimals. So I have to do something with that. So one way of doing that will be rounding the numbers. So we have our minimum, it's 6.6. We started with that, but we are not forced to start with that. We can start with any number and end with any number as long as all of our data are inside the interval. So I will just go and make our starting point 6. So I just take this and rounded it down. But if I start with 6 and if I will have 7 intervals with size 4, I'll finish at 34, and this number will again be outside. So I will round up the size of the data bin. I'll make it 5. Okay, so then our first interval will be starting at 6 and all the way up to 11. Next one, 11 up to 16. 16 up to 21. 21 up to 26. 26, 31, and 31 up to, oh, okay. Now we have another problem. We have 6 intervals instead of 7. But okay, it's not such a big deal. We will see why in a moment. So we have 1 less interval than recommended, but our numbers are pretty now, so more appropriate for human beings. And now we will count. Again, we can do it manually. We can find every number between 6 and 11 and count them by hand, but instead I'll ask Excel to do that for me. So I'll tell Excel, take all the numbers in this range which are more than or equal to 6, and all the numbers again in the same range which are less than 11. So I guess I did it properly. It's a long time, but I guess, yeah. So six numbers. Well, I'm not totally sure which 6 numbers it is, but maybe, okay, 1, 2, 2 for now, 3, 4, 5, and sixth one is 10 point something. It's somewhere there. Yeah, okay, so it looks all right. So we counted that. We go to the next row. We do the same thing, but the boundaries are different this time, 11 and 16. And the same thing here. So 16 up to 21. And here, 21 up to 26. And here, 26 and 31. And the last one is here. So 31 and 36. Okay, so we have our, well, it's not a frequency table like here, but it's something close. But instead of the entries, instead of the separate entries, we have intervals or data bins, call it what you want. Both names are used. And then we have frequencies here. We can again move to percentage if we want. So let's find the total first. It should be 150, but let's check. So the sum of all those numbers is, yeah, 150. Okay. So I'll take each number and divide by 150. All right. That was kind of a long ride, but we are there at least, at last. Yep. So this table, it also has its own name. So it's called frequency distribution. Frequency distribution. So going back here, when we had frequency table, we were able to build a frequency polygon. Yep, like that. We just took each entry, 0, 1, 2, we put them on x-axis. We took the frequencies and put them on y-axis and made a graph. We can do something, same thing here, but there's a question. What shall we put on our x-axis? Here we had separate entries. Here we have intervals instead. So what shall we put on x? Start of the interval, end of the interval, or something in between? So the standard way is using a midpoint of an interval. So the dead middle, the center of each interval. Well, so in this case, for this one, it will be, let me check. So 6 and 11, 17, 8.5. And the next one will be 13.5, 17.5, 21.5. Oh no, I'm doing it wrong. 18.5 and 23.5, 28.5. 33.5. So I found the center of each interval. I will just repeat the frequencies here. It's not necessary, just to make my own job easier. I'm copying them there. And then I do the same kind of plot. The only difference is that instead of the entries themselves, I have the midpoints of the intervals. So if you have a data set with distinct separate entries like here, yeah, you have these 6 numbers and nothing in between, you use the frequency table and frequency polygon with entries as x points. If you have something more like this, where your data is continuous and can go anywhere in between minimum and maximum, then instead of the entries themselves, you use data bins, so the intervals, and you have some freedom in choosing the intervals. Yep. So if we took the minimum and started with that and chose the minimum size of data bin, we would have these intervals. But instead of that, we rounded this down, we rounded this up, and we got these intervals. So you can make some small changes to make your data more convenient for perception by human beings. But your changes should be small, of course. So this is okay, but if instead I did something like starting with 0 and going all the way to 100, that won't be good, because our data will be just a small portion of that and so on. Okay, but when you have this continuous data, you use frequency distribution instead of a frequency table, and you can still use the polygon. One more kind of graphical representation is a histogram. I'm not sure if the histogram will work here in this case, but let's try. Okay, here it is. Yeah, it did only 3 data bins, and so we are losing some information. But I suppose that here it will be better. So let's try insert and histogram. Okay, it's doing its dumb thing still. Well, okay, so off with histograms for now. If you do it in desktop version of Excel, not in the online one, it will be better. Most probably it will have 7 data bins, and you will be able to change the settings. There is no way to change histogram settings here, but in desktop Excel you can select your data bins, the number of data bins, where to start, where to stop, and so on. So in that case you will have something more like this. Well, just instead of a continuous line you will have these steps, but there will be 7 of them, and the overall shape will be like this, like the bell curve. Okay, I guess that's too much for one day. Yep, so Let's do a quick recap. So
I
we
have a
have a,
question.
yep,
In data bin,
sorry?
in data bin,
Okay, so data bin.
yeah, actually, I didn't understand when we were talking about the decimals. Why we did like from 6.6 to 10.6. I mean, the last number is 6 in each of these numbers of
Oh,
the
so
decimal. Why
yeah,
was that?
so look here. You have
Yes.
this number 4, which is the size of data bin, and we got it
Mm-hmm.
by dividing our range by number of data bins, right? So
Uh-huh.
28 over 7 is 4. And now what I'm doing is I'm taking this as a
Uh-huh.
starting point, 6.6, and I'm adding 4 each time. 6.6
Ah,
plus 4 is 10.6. 10.6
uh-huh.
plus 4 is 14.6, and so on. I'm doing the same here, but first I changed, I rounded this down to 6 because I want the integer numbers. They look pretty and they are more convenient to work with. And I rounded this up because if I didn't do that, if I start with 6 and still use 4, then I won't cover all the way up to 34.6. My last number will be 34 and I will lose this one. So to encompass it, I made the size of data bin a bit larger. I made it 5. And now I can have all of my numbers inside my intervals. However, that lead us to lose something. So instead of an optimal number of 7, we have only 6. We could have had 7 if I took 4.5 instead of 5, but then I will again have decimal numbers and I don't want them. So sometimes you will have to do this kind of trade-offs. I will do this better, but this will get a bit worse, but okay, I'm okay with that and I will bear with that. Yeah, but you are just taking the starting point and adding the size of data bin each time.
Yeah,
And what's that doing
but
for
what
us?
about the maximum number, which was
Maximum? You mean this one?
yeah, 34.6, yeah. And in data bins we had 36, the maximum.
Yeah, that's
Should that be
because,
just like more than 34 and 6?
sorry?
Should the maximum number in data bins, I mean, here is 36, and it's more than 34 and
Oh,
6.
yeah,
Should that
yes.
be more?
Yeah, that's right, but that's okay. So what you want is, just a moment, let me go back to my drawing tool. So what you want is, so you want your data to be inside those intervals.
Yes.
You can do it in different ways. And our first one, when we started with 6.6 and finished at 34.6, was like, so here is your range covered by data bins, and maybe this one is your data. And it was a very tight fit. So the boundaries of your range were the same as boundaries of your data bin. In our second case, where we started with 6 and finished at 36, we have something like this. So this is our data, and we have excess spaces here and there, and that's okay. So both this and this are all right. What you don't want is something like this, where your data, oh, how did it get? Okay, it's zoom, I guess. So what you don't want is something like this, where your data is larger than our intervals. So if we started at 7, for example, if we started at 7 and finished at 30, that won't be okay, because that will leave these parts of our data outside. We will lose them, and we don't want that. But if we just have some excess spaces, so we have all our data inside and we have something more, it's all right. Having more is good. Having less is bad in this case.
Mm-hmm.
So the only condition, the only hard requirement is do not lose the data. We are not losing data here in this one, but we are losing it in this one. So we can use this, which is very tight fit. We can use this, which is a bit more loose fit, and we cannot use this because we will lose the data in that.
Got it.
Nice. Any more questions?
So there are kind of three types of illustrating these numbers. Am I right?
Oh, well, in fact, there are more.
There are more.
Yeah, we only stopped on these two because they are important. So they are conveying the information about the frequencies. But you can do the same thing using, for example, pie charts.
Bar charts.
Pie charts, well,
Line graphs.
just a moment. I'm not sure if I can use this to create a pie chart, but I will try. I don't like pie charts much, but okay, yeah, it's here. Something like that. You can use it too. It won't be as informative as the table or the polygon, but it will be more, what do you call it? Well, first of all, it will be more pleasant to the eye. And second of all, it will convey the same general understanding to the person that's looking at it. So I might not be able to find out the exact numbers from this, but I still can see that, for example, option 3 is encountered about 4 or 5 times as much as option 2, and so on, looking at those parts. You can use pie charts, you can use histograms, you can use something like maybe bar chart and so on. So there are many ways. There are many ways, but in their foundation, they always have either a frequency table or a frequency distribution. And you use frequency table in the cases where you have discrete data with separate entries, and you use the frequency distribution when your data is continuous. That's the only difference between those two.
Okay.
Next class on Thursday, we will look at how to calculate some measures of those data sets, like like average, mean value, and so on, and how to use probabilities for that, and also how we can do that in approximate ways using these frequency distributions. Sometimes it's more easy to find an approximate one, and the trade-off is good enough. But we will come to that on Wednesday.
Yeah.
Okay, and I think that's enough for today.
Yes.
It was a hell of a lot of
Sure.
info to to digest it for one time. But next classes I will try to portion it in smaller chunks. Sorry, guys.
I think a lot of course students are sleeping right now.
Oh, well, to be honest, I myself am almost sleeping right now.
Okay.
Start of the course is always kind of boring and kind of tedious. Just like with, for example, if you take the maths, right at the start, you learn how to count and how to add numbers and how to subtract them. And it's also boring, and it's always kind of hard both to learn the basics of the course and both to teach, because it's boring. But bear with me. I promise you that after a week or two, we will start to see some interesting things.
Yeah, yeah, sure.
Yeah.
Okay, so then
Thank you.
thank you too.
Thanks, teacher. Very awesome.
Thank you.
See
Bye bye.
See you on
Is it
Okay.
our?
Thank you, teacher.
Oh, by the way, I have a
Thank
question
you.
Okay.
while you all are here. So we should have our next lesson on Wednesday at 1 p.m.
Mhm.
But it
Okay.
happens so that on this Wednesday, I have my report. So I'm doing my PhD thesis now, and I need to have my report on Wednesday at, if I'm not mistaken, it's at 3 p.m. So what do you say if for this Wednesday we start a little bit earlier, like maybe at 12 p.m.?
Okay, why not?
Okay.
Will it
It's
be
no
all right
problem.
for you? Do you not have any other classes or something?
No, no, no.
No,
No.
it's okay.
Okay, so for one time, for this Wednesday, we will have our class at 12 p.m.
Okay.
And then we will go back to our 1 p.m. schedule. Okay, thank you.
Thank you,
Thank
teacher.
you too. Bye bye.
Listen.
Have a nice day. Bye.
Have a nice day.
Thank
Bye-bye.
you, teacher.